Every sound we hear, every photon of light that hits our eyes, the movement of grass blown by the wind, and the regular beat of the tides are all examples of a wave. But what makes a wave a wave? How can waves be described in a manner that allows us to understand their basic nature and qualities? Let us all find out. But first, let us define what wave is. A wave can be described as a disturbance that travels through a medium from one location to another. It transfers energy, momentum, and information, but not mass. So wave does not move mass in the direction of propagation, but rather it transfers energy.
Waves. One of the first things we need to know about waves is there are two different types of wave. One shown here by waves in the sea, and the other one shown by sound waves. So how are they different? Well, first let's look at the sea waves. If we look at them represented with this slinky, we see that the vibrations are at 90 degrees or perpendicular to the direction of travel of the wave. These are called transverse waves, and examples of them are waves in water, waves on a string, or light waves. Now let's look at the sound waves again. Again, we see them represented by the slinky, but this time the direction of vibration is parallel to the direction of travel. These are called longitudinal waves, and the only example you really need to remember is sound. One really important thing to remember about waves is they only transfer energy from place to place, not any matter. And we can see that here by looking at a lovely rubber duck sat in a bath. As a wave goes through, the duck bobs up and down, but once the wave's gone, he's back to his original position. The wave has carried energy through, but it did not carry the duck with it. Finally, we need to know some key features of waves. First off, wavelength. A wavelength is the length of a full cycle of a wave, from one point to the next same point. It's easiest to think of as the distance from crest to crest or from trough to trough. And we measure it in meters, and it's given the symbol lambda, a nice Greek symbol. The amplitude is like the size of a wave, but we need to remember that it's measured from the equilibrium position, or the central line, to the crest, not from the crest to the trough. Finally, frequency, which is the number of complete waves to pass a point every second, and it's given the unit of hertz. So an example of this would be if 10 waves pass in 2 seconds, the frequency would be 5 hertz. Using these things, we can actually now calculate the speed of a wave using the equation speed equals frequency times wavelength, or to give it in symbol form, V equals F lambda. So there's a lot to learn here, but once you've learned these core concepts, it will give you much more confidence in the rest of the topic.
Sound waves. What is a sound? Sound is a vibration or disturbance that travels through any medium by transferring energy from one particle to another and can be heard when it reaches a person's or animal's ear. Sound is a mechanical wave that results from the back and forth vibration of the particles of the medium through which the sound wave is moving. Sound wave, in the other hand, is a pressure caused by the vibration of something in a medium that transfers energy, like air. But how does sound travels?
In our previous video, we studied that sound needs a medium for propagation. That is, it requires some medium to travel from one place to another. But how does it really travel through the medium? What happens to the particles of the medium? Let us find out. We now know that sound is produced by vibration. When the object is vibrating, it sets the particles of the medium around into vibration. In the process, the nearest particles to the source gets displaced from their mean or equilibrium position. They start to collide with the particles adjacent to them. The adjacent particles then also get displaced from their mean positions. They in turn do the same to their neighboring particles. This process continues in the medium till the sound reaches our ear. We see that we create some disturbance flowing through the medium. This is the way that sound travels through the medium. We see that particles of the medium are not traveling from the source to the human ear. It is the disturbance produced by a source which is traveling in the medium. The particles are merely oscillating from their mean positions. This disturbance created by the vibrating object in the medium is what we call a sound wave. But what does this disturbance look like? Let us study this with the help of a tuning fork. Here we take air as a medium of propagation. Here we have a tuning fork made up of steel. This shows the initial condition of the air particles of the medium when the tuning fork is in its original position, that is, when tuning fork is not vibrating. When we strike its prong on a rubber band, we start hearing a sound. How does the sound travel through the medium? The two prongs of tuning fork are vibrating. Let us concentrate on motion of one of the prongs first. Say the one on the right. When it's away from its mean position, it pushes and compresses the air particles around it. This creates a high pressure region, also called compression. This compression travels in the medium as a disturbance. Here the density is high. That is, the particles are very close to each other. When the prong comes towards its mean position, the pressure on the right decreases and keeps on decreasing further as the prong continues its motion towards left. This creates a low pressure region, also called as rarefaction. We see that at this point, the compression in the form of disturbance has reached this region. This rarefaction also travels in the medium as a disturbance. Here the density of particles is less. That is, the particles are far away from each other. As it continues to vibrate, we get a series of these compressions and rarefactions. This continuous sequence of compressions and rarefactions is what we call sound waves. Yes, the sound waves travel in the form of compressions and rarefactions. Instead of the tuning fork, if we take any other source of sound, say the speaker, then the sound waves generated by this object will also travel in the form of compressions and rarefactions.
Characteristics of sound waves. First is frequency. It is the number of vibrations of the medium particle per second. For example, if a particle of medium undergoes 200 vibrations in 1 second, then the frequency of sound wave is 200 vibrations per second. The SI unit of frequency is Hertz. So if a particle of medium is vibrating with a frequency of 200 vibrations per second, when this particle collides with the next particle, it transfers its energy to the next particle, causing it to vibrate with the same frequency. Next is time period. It is basically the time taken by the medium particle to complete one vibration or oscillation. SI unit for time period is second. So by shortening the time interval in which something occurs, you are increasing its frequency. And by increasing the time interval, you decrease the frequency. If the amplitude of sound wave is high, loudness is also high. Similarly, if the amplitude of the sound wave is less, loudness is also less. Lastly, we have the wavelength. It is the distance traveled by sound during one vibration of the medium particle. Resonance. Resonance is a physical reaction in a vibrating system whereby certain frequencies elicit oscillation at a higher amplitude than normal. So now let us find out what are the common examples of resonance. First on the list is the swing. Once when the swing reaches its natural frequency of oscillation, a gentle push to the swing helps to maintain its amplitude due to resonance. But if the push given is irregular, the swing will hardly vibrate, and this out-of-sync motion will never lead to resonance, and the swing will not go higher. Next is the guitar. In an acoustic guitar, when you pluck a string, it vibrates and transmits the sound energy into the hollow wooden body of the guitar, making it resonate and amplify the sound. Pendulum. The pendulum works on the same principle as the swing. If we push the pendulum, it will move back and forth. Continuous pushing at irregular time intervals will cause an increase in the motion of the pendulum. If regular pushes are given to the pendulum, its motion can be built enormously. The natural frequency of a glass or any other object is determined by its shape and composition. If the singer's voice hits the resonant frequency of the wine glass, a transfer of energy will occur. However, the full transfer of energy can cause shattering of glass. Have you ever noticed the walls and furniture of your home vibrating when you play music on a heavy beat? This is because the natural frequency of the furniture gets resonated with the frequency of the sound of the music, and hence causing them to vibrate. The bathroom is enclosed space and sometimes small. As you sing, the sound waves hit the walls more frequently, causing the wall to vibrate since the walls are parallel to each other. The reflected sound hit each other and thereby causing the wall to vibrate at their natural frequency, and the louder sound is transmitted. When we turn the knob of the radio to our favorite channel, we are changing the natural frequency of the receiver. The natural frequency of the receiver then matches the transmission frequency of the radio station. When two frequencies match, energy transfers occurs and we listen to the selected channel. The food is heated quickly in a microwave because of resonance. The radiations emitted by a microwave oven has a certain wavelength and frequency, and like all other objects, molecules of water and fat also have a resonance frequency. At a certain frequency, the molecules absorb wavelength and start vibrating, causing cooking and heating up of food. So we will now further discuss resonant frequency. So resonant frequency is the natural vibrating frequency of an object. It occurs when there is a transfer of energy of different types, such as in the case of a pendulum, where potential energy is transferred to kinetic energy. It's also the characteristic frequency of a body or a system that reaches the maximum degree of oscillation.
Okay, in today's video, I'm going to go over how to calculate resonance frequency for series RLC circuits. And resonance occurs in a series RLC circuit occurs when the capacitive and the inductive reactances are equal to each other. So we could simply write that down as just say that the capacitive and the inductive reactances are equal. We can show that graphically in this graph, which has a graph of the reactances, both the inductive and the capacitive, with respect to the frequency. As you know, the capacitive reactance is inversely proportional to the frequency. The inductive reactance is directly proportional to the frequency. So at some point for a given circuit, those two values are going to be equal to each other, and that occurs where those two curves intersect. And that means that the inductive and the capacitive reactance will be equal, and that occurs right there, and that will be for a given frequency in our circuit when the capacitive and the inductive reactances are equal for a single frequency. Now we can also show that with our phasor diagram. You know, we have our phasor diagram, we have the capacitive reactance on the negative x-axis, the inductive reactance on the positive x-axis, and we want to figure out the impedance. We add up those values. Well, when we add those two up, they're going to cancel each other out, and that means that the impedance is simply going to be equal to the resistance of our circuit. All right, now let's go and see how we calculate the resonance frequency. We're going to set the inductive reactance and the capacitive reactance equal to each other. Inductive reactance is equal to 2 times pi times the frequency times the inductance of the inductor. Capacitive reactance is 1 over 2 pi times the frequency times the capacitance of the capacitor. These two frequencies are obviously the same frequency, so first thing we're going to do to solve for that frequency is multiply both sides of the equation by f. That gives us 2 pi f squared L equals 1 over 2 pi c. Now I'm going to divide both sides of the equation by 2 pi L. That gives me that f squared, the frequency squared, is equal to 1 over 4 pi squared LC. Now I'm going to take the square root of both sides. That's going to leave me with the frequency is equal to 1 over 2 pi square root LC. If I take the square root of both sides, the square root of 1 is 1, the square root of 4 is 2, the square root of pi squared is pi, and I'm left with the square root of LC like that. So this is the equation we use to calculate the resonance frequency if we want our answer to be in hertz. If we want our answer to be in radians, then this is the equation that we use. Omega, the angular frequency, is equal to 1 over the square root of LC like that. So we can use either equation depending on whether we want to answer in hertz or in radians. Okay, now let's go through and do an example. These are the values I had from the previous videos I made on RLC circuits. We have an inductor with an inductance of 750 millihenries, a capacitor with a capacitance of 15 microfarads. I'm simply going to plug my values in for the frequency. Is 1 over 2 pi times the square root of 750 times 10 to the minus 3 millihenries, 15 times 10 to the minus 6 microfarads, and I just get that my resonance frequency for that circuit with that capacitance and that inductance would be set 47.5 hertz. Okay, now I like to just go through and check to make sure that the capacitive and the inductive reactances will be equal for that value. So I'm just going to plug my values in for the capacitive reactance, and I get 1 over, and that gives me 224 ohms. We'll do the same thing for the inductive reactance, and that also gives me 224 ohms. And I can see that those two values are equal to each other, opposite in magnitude. They would be, this would be minus, no, this would be a minus, this would be a plus. Add them up, and you get 0, as we can show on our phasor diagram like that. Okay? In that case, when I add them up, then the sum of the capacitive and the inductive reactance would be 0. Of course, I would have no phase angle. If I calculate the impedance, x is 0, so the square root of 0 is 0, obviously. Then I get the square root of r squared is r, and the impedance would be equal to the resistance of the circuit, which in the examples I've used is 150 ohms. Okay? And that's how we would draw the impedance vector if you wanted to draw that on there. Okay, now let's see. The next thing we're going to do is that's it. Okay, so thank you very much for watching. I hope you found that video helpful. If you did, please do all of the following 3 things. Subscribe to my channel, get all my excellent physics, chemistry, and math videos. Give me a thumbs up for this video and leave me a nice positive comment in the comment section below. Thank you very much for watching.
Different types of resonance. The resonant frequency of the system is given by this formula, m being the mass of the suspended weight and k is the spring constant. In the case of stringed instruments, if we considered a wave traveling along the string with speed, the resonant frequency is given by this formula, where n is the harmonic order and L is the length of the string fixed at each end. The equation used to calculate the electrical resonant frequency in an LC circuit is this, where L is the inductance and C is the capacitance. Sources of sound waves. Acoustic instruments. The piano wire, the drum head, and the xylophone bar vibrate in different ways, making waves in the air that we then hear. These instruments also have built-in amplification. The large body of the piano acts as a sounding board, making the vibrating wire louder. The wind instruments, on the other hand, work differently. They set a column of air into resonance, making strong vibrations. The instrument's valves change the resonant frequency and thus the pitch of the instrument. They usually have a layered opening to achieve natural amplification. Next is electronic instruments. Electrical vibrations are the starting point of sounds from electronic organs and synthesizers. Circuits create a variety of wave shapes that might mimic standard instruments or make a totally new sounds. Since wave generation takes place electronically, it is easy to make new sounds with many different effects. It becomes sound, however, only when the electric signal goes to an amplifier and speakers. Living things. Animals and humans make sounds through their vocal cords, their mouths, and other body parts. Vocal cords vibrate from air pressure, making sound. Insects rapidly rub their legs, wings, or other organs to make noise. In the jungle, parrot screeches can carry 4 miles. Muscles turn chemical energy into mechanical energy. Squeezing and rubbing body parts turn mechanical energy into sound energy. Machines. In industry, machines make sound in ways similar to musical instruments. However, machines operates at higher speeds and with more power than instruments. They can be designated with sound-absorbing materials to make them quiet, but they seldom designed to sound pleasant. Loud, rapid impacts of metal and stones make the percussive noise of a jackhammer. Metal parts, rubbing from friction, create the squeal of brakes, 50 ignitions per second, and the clatter of spinning gears make the roar of an engine. Lastly, nature. The energy released when falling water hits a beach makes the sound of surf. Lightning explosively heats air, sending sound waves we hear as thunder. Wind produced by heat from the sun makes noise through setting objects into vibration. Wind can howl against itself when it gusts.